The exact method used by ancient Egyptians to cut cores out of granite and hard stones like diorite has been the source of much debate. Debate in theory is fine, but at some point you just need to get your hands dirty and start working at it. This video is probably going to make a lot of people angry, but I assure you that is not my intention. You see, if you watched my last video on drilling granite with copper and hard sand, you'd know that setup I used just didn't work. I needed a better jig to hold the drill in place, notches on my copper, lubrication, and a whole lot more. But I am not someone to let a good mistake go to waste, and I learned from it. Now, just so everyone knows, I am building a maximalist effort granite drilling machine that will be human powered and within the mechanical capabilities of the ancient Egyptians. But it isn't done yet, and I wanted to break this overall problem into chunks. Before spending all day trying this by hand, I needed to know for myself if it was possible at all to cut granite with sand and copper for a bit. Yes, many others have done this and said that it works, but I am on my own journey here and wanted to redeem myself after that last failed attempt. To that end, I realized the first thing I needed to do was correct the mechanical connection of the copper tube to the wooden shaft. Luckily, I have a perfect tool for centering various parts, and using my lathe, I drilled a hole in one end of a piece of oak. I used this red hole saw bit as it was pretty dull from lots of use. I would have thrown it away anyways, and it was the right size. Next, I used my modern vise to push this modern type M copper fitting onto the end of the oak. I already know it's not the right kind of copper, but I have not been able to find any metal dealers online who sell copper or bronze tubes with arsenic in a small quantity. So, if you are lucky enough to have some laying around, send me a message and donate it to my cause. I will gladly use it. Something that many of you pointed out in my last video that made sense to me was to make some notches in the pipe edge, and I was certainly going to try that if I had gotten that far. This time, I started out with 4 notches, each cut about 1/8 inch deep. Why 4? Well, 4 didn't seem to be so many notches that it would compromise the copper and make it roll over, but it would be enough to let sand and water flow in each side. Next, I needed to keep the copper pipe from coming loose, so I used some copper wire through the middle to anchor it. Bending the ends over on each side and crimping it securely, I used modern 2-part epoxy to connect the hole saw to the oak because, guys, it doesn't matter. The test will be of the cutting edge and abrasive versus granite, not the mechanical strength of JB Weld versus ancient Egyptian hide glue. That's not what I'm testing. I realized last time that carving that initial groove was not within my stoneworking capabilities, so for this, we will have to just be content with the bit being held in place by my drill press and then the stone secured from moving with clamps. Even so, this will still be a pure test where it actually matters. A copper cutting edge attempting to cut red granite with just hard sand abrasives that were available to the ancient Egyptians. The only variable here will be how long it takes. My drill press hopefully shortening days into hours. I mixed up my abrasives with a bit of water and just got to it. There is no book or manual precise enough to learn this without doing. I am fine with reading and all, but eventually if you want to learn something, you just have to put the books away and start trying to make it work. So maybe I'm adding too much or too little, too wet or too dry, but these are all tricks of the trade I will learn as I'm going along, and at the end, failures and all, and no matter what the outcome is, I will have learned more than when I started. I rigged up a weight hanging from the handle of my drill press that weighed a couple pounds. Enough weight to keep the bit at the bottom, but not enough to create unnecessary downward force. This allowed me to very simply automate my drill press and let it run for hours at a time while I did other stuff around the shop. It got a bit hot at the beginning, probably because the copper bit wasn't very deep into the water slurry mix, so I just kept giving it breaks and adding fresh grit and water as needed. As I learned later, the drill needs a bit more babysitting than I gave it at first, but it was indeed cutting into the granite. How far? I wasn't sure. I resisted the urge to constantly take my rig apart to check, as lining everything back up might be hard, and I wanted a pristine drill core. I knew something was happening though, because lifting the handle up showed just how far the drill had descended, or, my big fear, how badly my softer copper bit was wearing out. It's over 100 degrees where I'm at, and inside my shop, my drill press was soon hot enough to fry eggs. So after about 30 minutes, I decided to shut it down and start again the next morning when things were cooler. The next morning, I came back in and refreshed all my grit. I used 2, maybe 3 of these little shot glass sized cups of sand, corundum, and emery to make a nice deep slurry. I figured more of the bit that was in the slurry the better, and cooler it would be. You can see just how far we have come in about an hour and a half. My lever arm used to be all the way up at the top, and now it's all the way down here. It's cutting much faster day 2, telling me the hardest part was getting the groove into the granite initially going. Like I said at the beginning, this is just an intermediate phase on our way to a maximal ancient drill press rig I'm working on. In case you are wondering what speed I am cutting at, it's at the lowest setting my little drill press will allow, 620 RPM, little pulley to big pulley. Soon enough, I had cut so deep it was time to take my drill and stone out to wash off and do the first progress check. So the teeth have been worn down. You can remember I had those slots in there before, and the teeth have been worn down. So I've lost maybe an 1/8 inch of copper so far. You can just barely see the edge of one tooth right there. So I'll recut the teeth. Wow, look at that. I've definitely cut a good hole, and it looks to be more than an 1/8 inch deep. So I got about a 1/4 inch hole, 1/4 inch core. No one ever said that the copper wouldn't be worn down. The whole question is which will win the race, the copper or the actual granite. Right now it looks like the hole in the granite is deeper than the loss of the copper, so that would mean that the copper is actually winning and not wearing down as much as the granite. Now if we're comparing my bit partway through before we get going again with this large bit used for cutting cinder block, stone, it's diamond encrusted, so it can pretty much cut anything, honestly. You'll see we've got the same notches on the edge to let that slurry in and out that we do on my bit as well. And once again, that frosted appearance showing that the grit is getting embedded in there. I don't know if you can see it on camera, but it twinkles as I spin it, and you can see little bits. We'll probably take a closer look at this under a microscope just to see if we can actually see any grains of emery, quartz, corundum embedded in there. And I'm also going to compare a drill core drilled by this one and a drill core drilled by this one, just to see the difference. Now, before we get back to cutting, you'll see I made one other change as well. My terracotta was starting to soften up, and so I'm sure the purists will say, well, silicone caulk isn't period, man. You got to use 5 pounds of beeswax. Yeah, but it doesn't actually matter. I'm just trying to make a moat to keep it from leaking all over my welding table and creating a big rust spot. So you guys will just have to look at some silicone caulk and deal with that. Terracotta is still the base, but I really just try to stop the leaks. Okay, so after about another half hour of drilling, I'm over halfway through the core, and my teeth are still on the copper bit. It's cooling off right now, so don't have it up here, but something I noticed was the copper doesn't seem to wear out as fast if you keep refreshing and cleaning out the groove and adding more grit. The copper seems to wear the most when I walk away for too long and it starts grinding against the granite itself without a cushion of pulp in between. So as long as I keep the slurry refreshed, keep adding fresh grains, it seems to do okay. Now look at that. It's really interesting. The groove is maybe twice as wide, maybe 3 times as wide as my bit is thick. The wall of the bit is thick. So a lot of that grit is just slurring around the side and hollowing it out bigger and bigger. And I'm super interested to see just what kind of core it looks like. You can see some grooves on the inside there, but I won't be able to really tell what they look like until I get out there. That big groove, I think, is from when I took it out this morning and reseeded it. Obviously, it's impossible to get exactly in the same spot, so I think it probably won't be a perfect core, but I'm sure we'll have some, at least, grooves to look at. So we're going to go back to it. Okay, we've been drilling for about another hour, and it's time to check in and see where we're at. It's looking good. So I will say I've lost a lot less copper this morning than I did yesterday. And I think part of that's because yesterday I was kind of setting it and forgetting it, walking away for half an hour at a time. This time I'm paying a lot better attention, refreshing the pulp every 5 minutes or so, listening for audio changes, and you can tell when it becomes smooth in there, and you can tell when the grit wears out. It becomes a lot quieter. So I'll throw like a teaspoon in and try to keep it going. So I've only lost probably total 3/16 worth of copper, and as you can see, I've gone quite a ways in. Just to measure the best I can, it's about that deep. So let's see how much of that. So I've got only about a 1/4 inch from the bottom. So I've gotten, this is about an inch, 3/4 inch through, and I've only got a 1/4 inch left of that core. So I think total we've been about 2.5 hours, 2 hours and 45 minutes at the most. I haven't been exactly timing it, but it's been about that. No more than 3 hours at the very, very most. And we've gotten 3/4 of the way through this. So obviously it's way faster than doing this by hand, but the copper is holding up surprisingly well, even though it's not arsenic copper. It is softer, but the copper is holding up. The grit is doing beautifully. And right now I'm using emery and corundum, and it's doing really good. So quite excited with this progress. Okay, so we've drilled about as deep as we're going to get. We're a little bit over 3/4 of the way through, but I'm having to stop, and here's why. My bit's holding up great. As you can see, that second set of teeth is maybe degraded by a 1/16 at the most. Doing pretty good, but I've bottomed out. You can start seeing some shyness in there. And if you look at the plug that's left, you can see I've started chamfering the edges, which is actually kind of cool, but I'm not trying to round this whole top off. So it's cut in just over 3 hours, 3/4 of an inch. And I think that's pretty good. And what I'm going to do next is I'm going to just slice this right here. I was thinking about taking this piece of bronze I've got, since everyone gave me so much heck about using a steel chisel. Had this very sharp piece of bronze, so might cut my fingers doing this, but my plan was to pop it out, but I'm afraid I'm going to damage the core, and I really want to be able to look at that under a digital stereo microscope and see those lines. So I really want to preserve that core. Yes, I am interested in the lines on the inside as well, but I really want to see that core. I've cut one out of marble as well, just as comparison with a diamond bit, and we're going to look at those lines and compare them to these lines. So what I'm going to do is I'm going to cut this out with a diamond saw, and then see if I can free that core. Okay. Oh, that just popped right out. Oh, that was a little scary. Barely touched it, just popped out. See if I can. Oh, it's terrifying. Man, I've got some nice grooves in there, but can't really tell too much so far. I really don't want to break it. I'm just gonna clean this up a bit. And then I'm gonna put this over it and just try to pop it out. And there we have it. Far from perfect. You can really see where I did last night and where I changed it over right there. It's a bigger line. Man, the lines are very fine. Very close together. It'd be really interesting to see this dried off and under the microscope. So that's what we're gonna do next. I cleaned up both the core cut with my diamond drill bit and the one cut with sand and copper and put them under my digital microscope. By putting light at a right angle to the core, the grooves became much more visible. I observed that the core was quite a bit narrower at the top than at the bottom, as you can see here. I took numbers in 3 locations, top, middle, and bottom, and you can see that the core narrows toward the top. Granite is composed of many crystalline structures and inclusions of various types and hardness, not one uniform substance. As such, there are times, like right here, where an inclusion of quartz at the side of one of the cuts was in the way, and the drilling speed slowed, making finer grooves. Faster cutting when I was switching the grip more rapidly on day 2 made nicer grooves toward the end. The most critical observations, in my opinion, have to do with the taper toward the top of the core. Being so much thicker than the copper blade, and thus not possibly cut by it, the taper shows that the rotating slurry on its own on the outside and inside of the copper cut the grooves just by spinning around and around. The longer the core, the greater the taper. This is exactly what we see in numerous granite and other hard stone drill cores in museums. The tapered end is the top of the core, not the bottom, because the top has more time and exposure to the abrasive pulp, which wears it down. This taper is not possible to achieve with a drill that has teeth set like diamonds, as we will see here shortly. There is no core drill on this planet or any other that starts its cut at one size and then expands itself as it goes down the cut, making a taper that expands towards the bottom and shrinks toward the top. Comparing my core's grooves to those drilled in ancient Egypt shows virtually no difference, other than mine are very much finer in some cases. This is no doubt due to my faster rotation. Let's look at the famous Petrie core number 7. The smooth finish and taper tells me that this end is the top end of the cut. While none of the pictures online are in as high resolution as I would like, even so, we can see variation between the grooves. Here we have a nice wide fat groove, and here we have them much closer together. The difference is emphasizing that there is irregularity due to encountering various inclusions in the stone that slowed the cutting down, or times when fresh grit was added, speeding the cutting up at that point. There are at least several locations where we can see with our own eyes that the grooves on the Petrie core converge and then diverge. You can see the same behavior on my core. The leading edge of the copper drill with its bit is cutting in a straight line when viewed from the side, but as it wears into the stone, there is downward motion. Think of how many revolutions per minute were happening with my core. 620 revolutions per minute, and yet there are far fewer grooves than there are rotations. Thousands and thousands of rotations went into making a single groove. To say the grooves on my core or any other are threads would be to ignore everything that actually goes into making a thread. If you have ever used a thread cutter, you would know that once the thread gets going, you are going to cut it at the pitch of the cutting tool. A single pass cuts the thread. If the threads converge or diverge, that is a failed thread. I am not claiming that anyone has said the core was designed to be threaded, just that if you have actually cut threads yourself, you would know that the pitch of the thread and the spacing isn't variable like you would see on the Petri core and doesn't cross over itself, unless of course it's a failed one. Also, why only talk about the Petri core? It is certainly because Petri had his own speculation about its production, and while in many ways I love that Victorian explorer's work, here we see how someone with the stars of the Industrial Revolution in their eyes made a misstep and started some unneeded speculation. Go to the British Museum's website and you will see dozens of other cores like this one made of granite without any noticeable grooves. Most of them are cut out of much softer stones, and these had the same taper as well. Granite was cut, but it wasn't cut the most. It was only cut when absolutely necessary. Now let's take a look at the core I cut out with a diamond hole saw. It is extremely uniform in its thickness because no abrasive slurry was spinning around for hours and hours to make a taper. I took the same 3 measurements at the top, middle, and bottom, and as you can see, there is far less deviation than in my core. I washed off both cores to remove any dust and grit, but you will see that the diamond core is much whiter and less polished compared to the copper cut core. This is because, as I mentioned before, granite has many crystalline structures in it that crush and fragment under pressure. I drilled this out as rapidly as possible in about 5 minutes with water as a lubricant. Doing it fast with a lot of downward force did not create perfect threads as many would claim, but rather crushed the stone and created rougher grooves. The idea that any core of granite could be cut with any tool at 1 revolution per groove ignores the fundamental structure of granite. Tons of downward force on a cutting tool would not only cause it to overheat instantly, but it would also blow the granite into dust, not cut perfect threads. The slower cut core was of a much nicer quality as compared to the diamond cut core. Think about polishing a stone in a rock tumbler. You leave it for a very long time because all that tumbling and all that abrasive very slowly makes a beautiful surface. It takes time to polish granite. Now, if the Petri core was cut 1 revolution per thread, there is no use case that anyone has ever proposed for why a granite core itself would need to be cut in 1 revolution per thread. The hole was what was wanted, not the core. The cores were thrown out and are found discarded. Why would such a clearly massive machine able to create these cores be needed if the end product was a tapered core? The tapered core means it isn't perfectly machined. If you were trying to thread a bolt for some reason into a tapered hole in the stone, it would just bind, and all the stone cores are tapered. You can't have it both ways. You can't both have fast downward pressure, 1 turn per thread, and have the core be smooth. You can't be doing advanced machining and have both the hole and the core be tapered. Advanced, faster tools like this diamond bit make straight holes. Everyone has been looking at the grooves and ignoring the taper. Now, before we wrap up this chapter, I want to show you the end state of the softer modern copper tool. I lost just over 1/8 of copper in the first 1/4 inch of granite cutting, probably mostly due to my inexperience, and only about 1/16 in the last 3/4 inch of granite as I was adding abrasives every couple minutes to keep that pulp fresh. This amount of copper wear is acceptable and probably would be even less at a lower revolution per minute. Take a look at the frosted portion of the bit. The sand and parts of ground up granite have roughed up the surface and embedded chunks in the metal. I've also washed this several times, and yet it twinkles like a disco ball when rotated in the light. I cannot be sure if it's sand or quartz from the granite that sparkles so, but at any rate, the roughed up metal was able to keep the abrasives spinning without wearing out before the granite. If you look at the edge of the cutting tool, you will see that it's also tapered. The way the edge wears down brings the copper to a very fine cutting point. Once abrasive is put under that fine edge, it is forced into the granite at far more pounds per square inch, scoring it away. Remember, the Mohs hardness scale is not related to the hardness of the stone itself, but the relative ability of one mineral to scratch another. Now that I know for sure sand and copper can cut granite, I will be moving forward with confidence in building a fully hand-operated machine and seeing how that core turns out. Thank you for watching.